One of the things you can do is find out whether one node is a descendant of another node. And for that, you can use the isDescendantOf method. And that just simply returns true or false. So here's some code that gets a reference to the Phil Ledgerwood node, and then uses the isDescendantOf. Notice that this is an instance method, so it's a method of an existing hierarchy ID object that's in memory. So it's just checking to see if the current node is a descendant of Phil Ledgerwood. And so this is going to execute against all of the rows in the table, and it will filter the results to return only the descendants of Phil Ledgerwood. So as you can see, the query correctly identified that Jan and Wally are descendants of Phil Ledgerwood. But it also shows that Phil Ledgerwood is a descendant of Phil Ledgerwood. That's a little bit strange, but you just need to know that SQL Server considers a node to be a descendant of itself. If you don't want that behavior, you could filter out the parent node by modifying the where clause. Okay, you can also use isDescendantOf within the select statement in order to return all rows from the table and include a field to indicate whether the node is a descendant of Phil. Execute that code, and there you can see that me, Ken Getz, and Doug Ware are not descendants of Phil, but Phil is, Jan and Wally are, but Martin is not. And so, once again, we can look at the hierarchy diagram, and you can see that only Phil, Jan, and Wally are descendants of Phil, as SQL Server defines a descendant. Now, one of the interesting things about this query in particular is to notice the order in which the queries returned the rows. So it started at the root node, then with Ken, then with Doug, then with Phil, and then it included Phil's children, Jan and Wally, and then went up and grabbed Martin. So remember that that is depth first. Absent any reason to use that other index that we created, it's using the clustered index on the hierarchy ID column. And so that, by its nature, is a depth first index. And that's why the data was returned in that particular order. All right, you can also look at the ancestors of a node using the getAncestor method. And here's some code that does that. The parameter to this method indicates how many levels above the node you want to examine. So in this code, it retrieves the parent of the Wally node. It's a parent because it's going up one level. And I'm selecting the Wally node. Okay, so when I execute that, you can see that Phil Ledgerwood is Wally's parent, at least within this hierarchy. And then you can get the grandparent of the Wally node by passing a 2 to go up 2 levels. And there you can see the grandparent is me. I'm not sure I'm old enough to be a grandparent, but so be it. And taking it to one of its logical extremes, you can also go up 0 levels. So the only difference there is I'm going up 0 levels from the Wally node. And as you expect, that returns Wally. Okay, with all of the methods that are available in the hierarchy ID data type, you can usually do the same thing in several different ways. That's definitely a recurring theme in a sophisticated database project like SQL Server. So, for example, this code here shows a more concise way to insert a new node between the others. In the previous code, I wanted to make it explicit what was actually happening, but this is a more concise way of doing it. So the code gets references to the 2 nodes between which I want to insert the new node. And then these are the previous and following nodes, so that's going to have Jan and Wally. And then the insert statement uses a combination of the getAncestor and getDescendant methods to put the new node, Frank Tillinghast, between Jan and Wally. So a little bit convoluted, but in a lot of situations, it makes for a little bit cleaner code. And I'll execute that. And now you can see that Frank was inserted between Jan and Wally, and SQL Server added that .1 in order to keep the hierarchy intact. All right, you can also move nodes around a hierarchy. But this is one area where SQL Server provides relatively little automated support. You have to write the code to enforce the integrity of the hierarchy, or else create constraints on the table to explicitly enforce its integrity. So here's some code that is going to move the Jan Franson node. So it uses the getReparented_value method in order to make the move. And that method takes a reference to the old parent and to the new parent. So the old parent is going to be the ancestor of the node, which is going to be Jan because I'm filtering on that node. So this is going to be Jan's parent. And if we look back at the diagram here, we can see that again that Jan's parent is Phil Ledgerwood. And then it also takes a reference to the new parent, who's going to be Ken Getz. All right, so I'll execute that code, and we've moved Jan, and we can once again look at the contents of the table, and now you can see that Jan is a descendant of Ken. All right, in a real application, you'd also have to write code to reparent any descendants of Jan. That is not going to happen automatically. Okay, then the last bit of code here is just a way that you can create a kind of graphical view of the hierarchy. So what this code does is it places a number of dashes in front of the node based on its level. All right, so this first statement uses depth first because it's using the default index. And the second statement returns a breadth first because it includes an index hint, what's called an index hint, telling the query optimizer that it should use this instructor hierarchy index. This is that additional index that we created on the table. And so when we run both of these statements together, you can see the results. And actually, it's a little bit easier to see these kind of results if I send the results to text. So I'll execute that again. There we go. And there we have the depth first. It's going to go from Don to Ken to Jan, back up to Doug and Phil, back down to Frank and Wally, and back up to Martin. And here's the breadth first. So it's going to include the root node, and then all the siblings of level 1, and then all the siblings of level 2.